Say that we have aliens visiting Earth, and they're pretty chill and just want to celebrate the new connections. They want to drop their party bombs somewhere along an agreed upon street, but don't want there to be too much crowding on either side. As a result, if they have data on where everyone is on the street, they pick the median location to make sure that the amount of people on either side of the party bomb is approximately balanced. However, if there is interference, this can cause the result to be off. This is the story behind Penn Math Contest Alien Party Bonus Round that we had during Penn Virtual Math Contest in November 2025 and Penn Math Contest 5 in April 2026. In this video series, we are going to discuss the different strategies, insights, and conclusions of this game. PBMC's Alien Party has Locust Walk split into M segments, labeled from 0 to M-1. Everyone then tries to broadcast the value of the segment that they are on. However, the atmospheric interference adds a constant K to every broadcast value, meaning that when the aliens receive the values and calculate the median, they get the median plus K. However, sometimes, this value won't make sense, so they will instead pick median plus K, mod M, which is called the target value. The aliens then drop the party bomb here, and everyone's absolute distance, or loss, from the party bomb is calculated. Those who are closer will make a profit, while those who are further away will lose money. These profits are made in a way such that the sum of all of them is 0. There are certain values of K that make the one-round case interesting to look at. If K mod M is 0, then there is no interference, and we simply have to pick the median. M over 2 tends to be the best guess in this case. If K mod M is small, then the interference will push guesses to the right, so people will guess slightly above M over 2, making the best guess slightly above M over 2. If K mod M is slightly below M, then the interference will push guesses to the left, so people will guess slightly below M over 2, making the best guess slightly below M over 2. However, other values tend to make things complicated, which leads to some base strategies. PBMC provided 5 base strategies for Alien Party, so let's analyze 4 of these for the one-round case. The 0 strategy simply puts 0 every round. This is usually not a good strategy. The random strategy picks a value between 0 and M-1 both inclusive. This is slightly better than the 0 strategy, but it's still not that good. The half strategy always guesses M over 2, regardless of what K is. This is a smart strategy that can only have a loss of up to around M over 2, while the 0 strategy and the random strategy can have losses up to M-0.5 because of true median. If the target is randomly chosen, then the half strategy will have a bounded loss, often making it a safe strategy to use. Finally, there's the in no way strategy, which guesses M over 2 plus K mod M. This assumes that the median will be M over 2, then adds K and mods M to get the guess. If the guesses submitted are random, then this strategy does very well in the one-round case, as many random guesses will make the median around M over 2. However, there are values of K that can make this strategy a bit questionable, such as if K is M over 2 or slightly above or below M over 2. This can make the in no way strategy guess 0 or M-1. Compared to the half strategy, the losses can be very large in this case, and if the median is a bit off from M over 2, then the in no way strategy can incur a very large loss during that round. Since the median is calculated using the true median, the maximum possible value of the target is M-0.5, and this is the maximum loss that the in no way strategy can get. Seeing this, one idea is to hedge the guess if K is close to M over 2, reverting to the half strategy. This can reduce the losses. After introducing the hedging idea, we started trying a bunch of variations of it. The main goal was not necessarily to maximize average profit, but instead to avoid catastrophic rounds where the strategy completely explodes because it guessed near 0 while the target ended up near M-1, or vice versa. Since Alien Party uses linear loss instead of squared loss, these disasters are not quite as devastating as they would be in something like least squares optimization, but they still matter a lot over hundreds of rounds. One simple idea was what we called defending. If the strategy was about to guess extremely close to 0 or extremely close to M-1, we would push it slightly back toward the center. Another idea was clamping, where guesses were simply prevented from going too far toward the edges. These strategies made intuitive sense. If you know that edge guesses can fail horribly, then avoiding the edges sounds smart. The issue is that alien party rewards being correct more than it rewards being safe. Over-defending often meant giving up the advantage that In No Way had in the first place. The strategy became more stable, but also less accurate. As a result, most of these defensive ideas ended up being slightly worse in practice. However, one hedge strategy consistently did surprisingly well, hedge if near half In No Way. The idea was simple. Most of the time, use In No Way. But if K was close to M/2, where the strategy becomes unstable and wraps around the modulo boundary, it temporarily falls back toward half instead. This reduced some of the worst edge case failures while preserving most of the strength of the original strategy. At this point, hedge if near half In No Way was one of the strongest strategies we had seen. But then we started noticing something else. A lot of strategies in my environment were beginning to look suspiciously similar to In No Way. Some strategies hedged it slightly, some clamped it slightly, some randomized it slightly, but many of them were still fundamentally centered around M/2 plus K. But if everyone is trying to predict the same thing, then maybe we should exploit that. This led to what was originally called exploit strategy, but later became known as the Penn strategy. Its formula is M/2 plus 2K, mod M. The logic is actually pretty interesting. If everybody else is effectively guessing around M/2 plus K, then the median of the guesses will also move toward M/2 plus K. But remember, the aliens add another K afterward, so M/2 plus 2K gives the new best guess. This strategy worked shockingly well. Against large populations of In No Way-like strategies, exploit often dominated because it was effectively one interference ahead of everyone else. While the other strategies compensated once for atmospheric interference, exploit compensated twice. But then we found its fatal flaw. Suppose K is around M/4. The In No Way strategies are still guessing relatively large numbers, because they are centered around M/2 plus K. But exploit becomes M, which wraps around to 0 after modulo. So suddenly, exploit jumps all the way from high guesses to low guesses. This creates a split population. The In No Way style strategies stay high, while exploit wraps around and goes low. The median often ends up somewhere in between, which causes exploit to completely miss the target and for the In No Way strategies to perform well. Mathematically, the instability starts exactly at K equals M/4. Empirically, the bad regions seem to continue until around K equals M/3. In this range, exploit could perform extremely badly. So naturally, we tried to patch it, and this led to the Lorelei strategy. Lorelei basically says, if K is in the dangerous zone between roughly M/4 and M/3, stop trying to exploit everybody and just go back to In No Way. Outside that region, use exploit normally. This tiny adjustment ended up working remarkably well. Exploit handled the environments dominated by In No Way-like behavior, while Lorelei avoided the catastrophic wraparound failure zone. And somehow, despite being an extremely cursed-looking piecewise strategy, it consistently performed near the top in simulations. Usually by an annoyingly small amount. At this point in testing, hedge if near half In No Way and Lorelei were generally the two strongest strategies we had found, with Lorelei often barely squeaking ahead. But then we started thinking about something bigger. So far, almost all of these strategies were one-round strategies. They only looked at the current values of M and K. But Alien Party is actually a repeated game over many rounds. And that raises an important question: what if the previous rounds contain information? This leads us to the copy strategies. The simplest version was extremely straightforward: take the previous round's median, and guess that again. At first glance, this sounds very reasonable. If the player population is somewhat stable, then maybe the median stays relatively stable too. The problem is that Alien Party changes M every round. Suppose the previous median was 900, but now M is only 50. Suddenly, that old information becomes almost meaningless. Raw medians do not transfer well across different scales. So the copy strategy ended up failing pretty badly whenever M changed significantly between rounds. To fix this, we tried ratio strategy. Instead of copying the raw median, we scaled it proportionally based on the old and new values of M. If the old median was 75% of the way across the street, then the new guess should also be 75% of the way across the new street. This makes mathematical sense. It preserves relative positioning rather than absolute positioning. Unfortunately, players are not actually distributed proportionally from round to round. The scaling assumption often just wasn't true. Ratio strategy was definitely more sensible than raw copy strategy, but in practice it still tended to underperform the stronger strategies like Lorelei. We also tried to make a neural network trained using the genetic algorithm to try to adapt to the multi-round game, and this led to the neural network strategy. While it wasn't as good as In No Way, it would usually beat copy strategy and random strategy in this environment, so we decided to keep it as a base strategy and have people use it to help them with how to use state variables. At this point, I got bored and decided to ask ChatGPT to come up with a strategy, and it came up with the drift strategy. Drift strategies tried to identify trends over time. If the medians seem to be moving upward, maybe continue upward. If they seem to oscillate, maybe compensate for that. So this definitely sounds like something that would work. The issue is that drift often assume patterns that simply were not there. Alien Party has changing M values, changing K values, modulo behavior, nonlinear population reactions, and strategies actively adapting to one another. The environment is noisy enough that apparent trends are often just random artifacts. A lot of drift implementations also secretly depended on previous _median raw, which inherited many of the same problems as copy strategy. So while drift strategies look clever, they usually fail to consistently outperform the top simpler strategies. And that is honestly one of the funniest conclusions of this entire process. The strategies that looked the smartest were often not the best and would often lose to random strategy. Meanwhile, strategies with names like In No Way and Lorelei kept quietly winning simulations. And that brings us to the next stage of Alien Party. Everything so far has mostly been theoretical analysis, simulations, and one-round reasoning. But what happens during the actual Penn virtual math contest round? What strategies did people really submit? Which ideas survive contact with actual competition? And what bizarre behaviors emerge when people have to deal with hard-coded and random rounds? That's what we'll analyze in the next part.